So welcome to this lecture on quantum chromodynamics. So far we had studied about quantum electrodynamics. We had called it QED, right? So we had studied about QED. So there we had studied about electrons and photons, right? So electrons and the mediator particle, the force mediator particle, we had studied about the photons. Now we're going to study about QCD, right? So QCD, so electrons and the entire family of other leptons, right? So the other particles, like we had studied about the positron and every other particle in that lepton family, and we see that the force mediated by these particles is mediated by the photons. So similarly, what happens here in QCD, quantum chromodynamics? So here we are talking about the particles that make up the nucleus, right? We are talking about the quarks, the particles that essentially make up the protons and the neutrons. So we are talking about here fundamentally quarks. Okay, so some background on particle physics is necessary. So you might just read up on any particle physics book or on the standard model and just learn some basics. So here we have the quarks. Okay, so the quarks and the force mediated between the quarks is mediated by a particle called the gluon. Okay, so here we have this. Now here, just like for the electron, we have two electrons, and what is electrons are identical, but there is a way to there is a distinguishing aspect of the electron where we have a spin up and a spin down. So supposing you apply a magnetic field, if it is spin up, there is a force experienced in one direction, spin down it's experienced the other direction, right? So electrons, we studied about the spin, right? So here they introduced the spinors to essentially distinguish between an additional quantum number we had introduced called the spin quantum number, and we had introduced the Dirac spinor, right? So we introduced spinors to essentially quantify the state of the electron mathematically, an additional representation, okay, an additional mathematical tool to accurately describe the state of the electron. So here in quarks, in addition to the spin of the quark, okay, in addition to the spin, we're going to have another quantum number which is called the color. So there are going to be three colors: red, blue, and green. Just like we had two spin states, the color state is a three. There are three states: color red, blue, and green. So we're going to introduce another vector here, a column vector. So for red, blue, and green. So this is important. So here we have, in addition to spin, we have color. So this has to be incorporated in the mathematics. Okay, so that is what we are doing here. Now, so this is the Feynman diagram. So we've already worked with Feynman diagram, so we know what it is about. So here we have a red colored quark coming in and a blue colored quark going out, and the difference in the so they're interacting by exchange of a gluon. So this is the exchange of a gluon. So there we have studied about interaction by exchange of a photon, right? So we have drawn this line, this wiggly line. So there we had studied about electrons interacting by exchange of some photons. So here we are studying in exchange of gluons. So here the difference in the color is carried out by the gluon. Okay, so the difference in the color is carried out by the gluon. So at every vertex, the color is preserved. Okay, so that is what this means. So now for the gluon, we are going to have eight states of the gluon. Okay, so just like we have 8 states of the gluon, and we impose the Lorentz condition and we adopt the Coulomb gauge. So you can see now what is happening. In order to describe, so in quantum chromodynamics, we are we are taking the theory from quantum electrodynamics. So just to describe the state of the quarks, we had developed the Dirac theory, which described the particle with the spin. So in addition to that, we had introduced the color quantum number and the vectors to describe it mathematically. So here, to describe the gluon, we had already, for the photon, we had developed the Maxwell uh, field, right? So we had developed the formalism of the Maxwell field, and we had the gauge field. So it's called the gauge field. So in addition, so we had described it using this. So this was your, Maxwell field that described your Maxwell field that described the photon, right? So this was for the photon state described by the Maxwell field. So in addition, so the gluon field is also going to be described. We were going to borrow this theoretical apparatus from the Maxwell field that described the photon, but in addition, we are going to introduce the column vector, 8-column vector, to describe the color state of the gluon. So that is what we are doing here. So, and again, we are in. So we'd seen about the Pauli sigma matrices that were essential, the Pauli spin matrices. So we had 3 spin matrices, right? So the 3 spin matrices, sigma x, sigma y, and sigma z. So this is given by the, so this had a SU2 representation. So similarly, the corresponding matrices here are called the Gell-Mann matrices. Gell-Mann matrices, and here, so here these matrices have a SU3 symmetry. So again, this entails an understanding of group theory, okay, and particularly continuous groups. So here we'll talk about continuous groups. So now, if you don't know, for now, if you don't know watching these lectures, it's okay. But at some point, you'll have to look it up, and so that you'll be introduced to group theory and Lie algebras and Lie groups, so that you can also think and talk in the language of physicists. Okay. So here, what I'm saying here, this is actually called the. So these matrices obey this Lie algebra. Okay. So this is the Lie algebra that these matrices obey, called the algebra of the groups. And this F is called the structure constants. Okay. So these are your. So these Lie. So each element of this Lie algebra is called the generator of the group. Okay, so you might want to. So this is not the place for me to explain all this, but I'm letting you know these things are essential so that you may look it up and learn them up, so that you might essentially finally start thinking in terms of the language and the theoretical apparatus which physicists use to think about stuff. So now let's come to Feynman rules. So we had studied about Feynman rules in QED. So these are the Feynman rules in QCD. So essentially, Feynman rules are used to calculate the scattering amplitudes. So uh, they use the. So basically, it's nothing but Feynman rules is nothing but it captures the rules of perturbation theory, and it is used to calculate the scattering amplitudes. So the S matrix elements, and then we calculate the scattering amplitudes. So here we have for each incoming quark and outgoing quark, we have the spinor, and here is the C, which was the color vector. Okay, and here again we have for the anti quark. Okay, so Again, here for the gluon, here we have the in addition to what we had used to describe the photon, here we have another vector A, which is an 8th state vector to describe the color of the gluon, color state of the gluon. Okay, so again we have the propagators for the quarks and an anti-quarks and the gluon, and each interaction vertex will add a vertex factor. So this vertex factor was in your is this was your vertex factor in QED. So this was in QED. This is in QED. This is in QCD. Okay, so quantum chromodynamics, the coupling constant is going to be different. So each vertex factor will have a coupling constant, right? So this adds the coupling constant. So it tells you how much the quarks are coupling to the gluons. Okay, so here you can see in the diagram there is a vertex factor here. So we see each vertex factor introduces a coupling constant. So let us look at a diagram where we had essentially calculated the so any given Feynman diagram, we just apply the Feynman rules and calculate the scattering amplitude m, right? So we calculate the scattering amplitude m. This is what we calculate, the scattering amplitude. Because as I said, quantum field theory was first used in the case to calculate scattering amplitudes for processes that happen within the particle collider. So that is what we do. Now, let us look at some named Feynman diagrams, with names that have some special significance. Okay, when we use Feynman rules and they have come with a name because they have some special significance. So we looked at one similar we're going to look at this effect called asymptotic freedom in quantum chromodynamics. So before that we had looked at a similar diagram in QED, quantum electrodynamics. So when we had spoken about renormalization, we saw about these looped diagrams which introduce more number of vertex factors, because of which there is divergence introduced in the calculating the in the integrals, and you're doing the integrals, and then we do the process of renormalization, which makes the coupling constant a function of the momentum transfer during the process. So the Q is this momentum that is transferred by the virtual particle. Here the virtual particle is a photon. So the coupling constant becomes a function of the momentum transfer. So here you can see in QED, so this was the diagram that we saw. So we have the electron and the muon interaction. So in the electron and the muon interaction, there is a photon exchange. So two electrons are coming in. Okay, so two electrons are coming in and they're interacting, and there is a photon that is being exchanged, and there are two muons going on. So we saw that when they are the higher the momentum transferred in the collision. Okay, so higher you can from the diagram, from this equation we got this equation which gave us a relationship between the uh, uh, so the coupling constant is a function of q, the momentum transfer. So now as the momentum transfer increases, so here you can see as q increases, the coupling constant increases. So what you can make out of that is that when the momentum transfer is more, right? So when the momentum transfer is more, so as the momentum transfer is higher in any process, the charges get closer together, and therefore the coupling constant increases. So this is directly follows from this equation. As q becomes higher, the coupling constant value increases, right? So if the coupling constant value increases, this coupling constant is nothing but here. The coupling constant is written in terms of the fine structure constant alpha, which is nothing but E square by 4 pi epsilon naught h bar c. So remember that. So if coupling constant increases, then it means that the charge of the electron increases, right? So if the charge of the electron increases, then we interpret this as the vacuum polarizing the or screening the charge. Okay, so this is why it's called the vacuum polarization diagram, because we are interpreting now that the charge of the electron has increased. Therefore, before this process was happening, we interpret that the vacuum was acting as a screening of the charge by acting as a dielectric medium and reducing the effect of the charge. So we talk about the screening effect of the vacuum. Okay, so screening effect of the vacuum. So similarly, we are going to see an anti-screening effect here in the case of QCD. Okay, so here we again have quarks interacting, two quarks coming and then two quarks going out, and here instead of the photon we have the gluon, and this is a bubble diagram, and therefore we have to renormalize, and when we renormalize, the coupling constant is produced as a function of q, that is the momentum transfer. Now, here you can notice two things here in the diagram. Here we have another new factor n and s. So n is the number of colors. Okay, so the quarks have 3 colors, and they also come in 6 flavors. Okay, and in the standard model we have 3 and 6. So wherever 11n is greater than 2f, what will happen is anti-screening will dominate. That is the opposite effect of this effect will happen here in QCD. That is, the coupling constant will decrease with high Qs. That is, more the momentum transferred. Okay, so more the momentum transferred, the less the coupling will be. Okay, so therefore we say that this is called the asymptotic freedom of quarks. Okay, so this effect is called the asymptotic freedom of quarks. So we know that the strong force, right, mediated by the gluon, so the nuclear force is a short range force, and it binds the nucleons together. That means the quarks, they must have a attractive force that binds them together. But what we are seeing here is, as you increase the interaction between them, that is the momentum transfer between them, the amount by which they couple together is getting decreased. So so as you increase so as they come closer together at very close distances, the coupling between them, that is maybe we are talking about the attraction between them, is decreasing. Okay, so this is called the asymptotic freedom of quarks. So these are some name diagrams that we've studied about. So if you find our channel useful, please let your friends know about it and do subscribe to support our effort. Thank you.